Good morning and welcome to my stream. The sound seems alright. So I would say, yeah, welcome to day 7 of Advent of Code, and let's hop right into it. So day 7, the task is laboratories. You thank the cephalopods for the help and exit the trash compactor, finding yourself in the familiar halls of a North Pole research wing. Based on the large sign that says Teleporter Hub, they seem to be researching teleportation. You can't help but try it for yourself and step onto the large yellow teleporter pad. Suddenly, you find yourself in an unfamiliar room. The room has has no doors. The only way out is the teleporter. Unfortunately, the teleporter seems to be leaking magic smoke. Since this is a teleporter lab, there are lots of spare parts, manuals, and diagnostic equipment lying around. After connecting one of the diagnostic tools, it helpfully displays error code "oh no", which apparently means that there is an issue with one of the tachyon manifolds. You quickly locate a diagram of the tachyon manifold, your puzzle input. A tachyon beam enters the manifold at the location marked S. Tachyon beams always move downward. Tachyon beams pass freely through empty space, the dots. However, if a tachyon beam encounters a splitter, the beam is stopped. Instead, a new tachyon beam continues from the immediate left and from the immediate right of the splitter. So here we have an example input. Here from the S, the tachyon beam originates, and then each time such a splitter is encountered, the tachyon beams continues to the left and right. And this continues. I'm not sure if two splitters can be right next to each other, so that one splitter immediately splits again, or if that even happens. Let's search for it. We can actually search for this, and this doesn't seem to be the case. There are enough of those, but no immediate splitting happening here. That's good. Those were the inputs from yesterday. I just closed them. Yeah, so then I would say, and what is our task, of course? To repair the teleporter, you first need to understand the beam splitting properties of the tachyon manifold. In this example, a tachyon beam is split a total of 21 times. Yeah, and that's just how often a beam enters such a splitter. So we could simply follow the beam completely downward and count how many splitters it encounters on the way. Yeah, and we have to keep track which splitter we already visited so that we don't count them twice. That will be important. I'm thinking that that we actually, I was thinking how we can keep track of the ones we visited, and there are two options in my eyes. We can either keep track by using a set, or we can keep track by replacing the character with a different sign. But I just thought that that won't necessarily be necessary. Let's say we start here, and each time we move, we have a set of positions from which we start, and then our tachyon beam encounters this. And let's say there, let's use another position. This down here. Okay, it's yeah. Then let's go back up. Here, down in this position. Yeah, this is better. Down in this position, this beam and this beam will now, in the next situation, the first beam will split on this splitter and go to the right, while this beam will just go down. So at any given point in time, the tachyons will have traveled the same distance from S. No matter how often it is split, they are always on the same, or they are always on the same distance from counted from the top. So we don't actually need to keep a track of a set that has every single splitter, or we don't need to keep track of the splitters at all, because we can simply track the starting positions in a set, and then we can already be sure that we won't count anything twice. Nah. That is of course right, but we should always keep also keep a list of splitters we counted at the given position. So for this we create a new set and check. For this row we also create a new set and check, but there is no position here, so we don't count any splitters. And here again we count the splitters, just to be sure, because we cannot know the reason why a starting position isn't inserted. If it was already there, it could be that one came from the top, or that one used the same splitter as this one does. So, but as we are only counting the splitters, only one position can use a splitter, so it doesn't matter. So we don't have to use the list again, because let's go a little bit further down. Here at this position, there can never be two beams that use this splitter, because the splitter can only be used from right above it. So again, there's actually no use in keeping track of which splitters we already used by using a set. We can simply, we already know that a splitter will only be used once. Okay, then, I think we can work with that knowledge. Then let's take our test input and let's go over to Visual Studio Code and start with our day 7 implementation. Copy day 6 and day 7. Yeah, we can keep the num type we have here. That always works quite well, to just have a type that saves the number we are using for intermediate operations. So the rest can be deleted. We know we don't need that, and this will be 21 for now. Then let's head over to our module and let's initialize day 7 as part of our module and instantiate day 7 here. And it has to be imported, of course. And now we can go over to Brave, copy the input. I'm just doing it myself without taking the stream with me. Just not necessary for simply copying the input. Yeah, so that's it. Then let's get started with part A. Quickly taking a sip from my coffee. So, we have our input. So, let's first split this. Let's split it into a vector of chars, because I think that will be easier. We could, of course, keep it as a vector of strings, but I think as we are looking at single positions, I somehow think it is easier to have the lines as chars. Lim chars. Let's call this line. And let's say collect. That's our grid again. But this grid should be a vector of char. And here we also have to say collect, not chars. This should be working, looks good. So now we have to find our S. Grid at 0, is there a find? Will it return the index? Search for an element of an iterator certified as a predicate, takes a closure that returns true or false. Sum of the element. Okay, I mean, we can enumerate, and then we get the index. So enumerate, and then we say element, or let's ignore the index because we don't need it right now. So we have our element. Let's see, reference it, and then we say element equals S. Dot unwrap. This is our start. Now we don't need the element in this case. We simply need the index. So we can say ID X and ignore char itself. Not happy with me here. Then let's dereference like that. So now we have our starting point. Then let's make immutable starting positions. That is not how you spell that. I have to let my cat out. Be right back. So I'm back. This is how you write positions now. And then let's create a hash set. That is a semicolon. I'm not sure. Is there a set macro? Probably not. No. Okay. And then let's say insert. Yes, insert IDX. So now we have our starting positions. And now we can simply loop. Actually, I think we can use a for loop here. And we can go from 0 to grid length. I think it should be -1 in our case. And then for pause in starting positions, we should probably create next start pause hash set new. Not a must, just a mute. So we have a new starting positions, which we are going to fill when we iterate now. So, and now we have a pause, which is just a use size. That's actually not what I wanted. I wanted a tuple like this. then you also have to be a U size, otherwise this doesn't make sense. And then from the pause we have X and Y. So then we simply say if our grid at x plus 1 and y is equal to a splitter, then we do something, and else we simply say next start pause is x plus 1 y. We of course have to say insert and not just call it on the object. That won't work. So, and if it is the case here, then we get two new starting positions, both at a new x plus 1. New x is x plus 1, or we can actually just say x is x plus 1. Then we don't need this here. So one's minus 1 and one's plus 1. So these are our new positions, and we encounter a splitter, so we have to say let mute split count is equal to 0, and in this case we increase the split count by 1, and then in the end we simply return our split count. Actually, this could already be it, yeah, almost. Now we have to say starting positions is next start pause. The old collection is dropped and the new one is used. This could already be it. Yeah, this finishes the tests. Then I'm quickly going over to Brave and I'm copying the input for today. Then day 07. This is our input. Looks like a huge Christmas tree, and I bet that is intentional. Okay, day 7 seems to be loaded. Then let's simply run this. 1592. Then let's go over to Brave and check whether or not this is correct. And that's actually right. In how long are we streaming now? I can't see it anywhere. Never mind, but I think that is still a record. For me, at least. That was quite fast. 20 minutes. And there was some warm-up time for the stream. So, yeah, less than 20 minutes, maybe 15. Not bad. Okay, so part 2. With your analysis of the manifold complete, you begin fixing the teleporter. However, as you open the side of the teleporter to replace the broken manifold, you are surprised to discover that it isn't a classical tachyon manifold, it's a quantum tachyon manifold. With a quantum tachyon manifold, only a single tachyon particle is sent through the manifold. A tachyon particle takes both the left and the right path of each splitter encountered. Since this is impossible, the manual recommends the many worlds interpretation of the quantum tachyon splitting. Each time a particle reaches a splitter, it's actually time itself which splits. In one timeline, the particle went left, and in the other the timeline, the particle went right. To fix the manifold, what you really need to know is the number of timelines active after a single particle completes all of its possible journeys through the manifold. In the above example, there are many timelines for this. For instance, there's a timeline where the particles always went left, or there's a timelines where the particles alternated, going left and right at each splitter. Or there's a timeline where the particle ends up at the same point as the alternating timeline, but takes a totally different path to get there. In this example, in total, particle ends up on 40 different timelines. Apply the many worlds interpretation of the quantum tachyon splitting to your manifold diagram. In total, how many different times would a single tachyon particle end up? No, how many different timelines would a single tachyon particle end up on? Okay. So that seems more complicated. Yeah, let's see. Let's first. So we still need those two. So let's extract those into a function, and that is grid with start. We get our vector and we get our grid. It's good. We can then reuse that up here, and actually, yeah, we could also probably still use this kinda. So let's go back to the example once more and think about how we can actually achieve this. So we can, of course, fully enumerate that, but maybe I'm thinking if we can use a different approach. So, for example, we don't actually have to. So let's humor this. We go down here completely until here. If we now take this and go from here to the right, we don't actually need to enumerate this completely again. We only have to check this path. And from here, we only have to check this path, and from here only this path. So we can keep track and always split at such an index. Give me a second, the cat is once in again. Okay, so I'm back. So actually our timeline splits each time we reach such a splitter, and then we have to calculate both timelines. So if I'm not wrong, it's practically the same, but we have to count how many are walking that way. So right now, if there are two beams split onto the same field, like for example here, then we count this as one. But if we count that as two beams here, because both are going this way, then we can actually do that here again. And yeah, I think that's already it. The only difference is we should probably use, instead of a set, a map, and count in the map how often elements are there. that's already it. I think that should, if we propagate that information up or down, then, for example, here we count 2 because it is split into this twice. And then here, this will be created. This path will be, sorry. This path will be used twice from this side and once from this side. So now 3 paths go this way. And the same is here. Now 4 paths, 3 paths from this splitter go this way, and 1 path from this splitter goes this way. And this way we can just simply propagate that down until we are down here, and then we have our 40 elements. And I think this should get us to the right solution without writing a lot more code or anything. I think we simply need to change the data structure from a hash set to a hash map. And we start with 1 simple path, single one. And then we actually don't need a split count now, because we are not counting the splits, we are counting our results in the end. So you are not a hash set anymore, you are now a hash map. This is almost correct. I want to still split you into X and Y, but I also want to know your count, how often you were split. And this is simply count here and count here, but we cannot use insert now. Because insert would simply override it or even panic. No, it returns an option. Yeah, okay, but we need an update. So let's quickly look for the update function or something similar. An upsert. No. But upsert would actually be logical. Reserve, retain. We could of course get it and then put it, but I think there was a function which did what we actually want. Okay, we don't need anything from the iter trait. Contains key, sure. What is drain? Drain sounds interesting. Entry. We need something that takes a function. Extract if, get. Insert. That's just key value. Is empty. Iter. Yeah. Okay, let's do it like this. We say... Yeah, we can actually update the count, because the count will always stay the same, so the count will split left and right. But if there is already an element in it, then of course we have to increment by 1. Or we have to increment by the count that is already in there. So let's call this other count is equal to starting positions. I'm not sure if we are allowed to do that. No, it's next start pos, which we need. A get, and then our let me think. I don't want to mess this up. What do we actually need to get here? Let's go back to the drawing board. I think that's a good idea. So when we split, so when we split here, the count, we simply insert it because there's no element here yet, so it's 1. And here, so we have to check that for each element by itself, of course. So we probably should simply make a function that we call upsert. Maybe there is already that function and I just am unable to find it right now. Hash map of usize. Let's type pos is equal to usize, usize. If that's a good idea to use that. So pos and char is our map. I don't know why. Yeah, because I thought I had to use two of them. Then why aren't you happy? Because I used the ampersand at the wrong position. You're still not happy with me. Hashtag struct takes at least two gener. Yeah, of course, because that is how it's actually used. Yeah, okay. So then we have a position of type pos, and we have our count of type usize. It's actually not on a char, it's on an I61 num. Let's just say that it maps to num. Then this is also num. So, and now we say map.get pos match some count is already in here. Now I shouldn't override count. Old count. Then we get old count plus count. And if it's none, then we simply get count. And then we simply say map dot insert is pos, and the value is the result of our match statement. And now you probably need to be made mutable for this to work. And your problem is that you just need a reference. Yeah, but then the insertion doesn't work, so we use a reference here. What's your problem? Cannot borrow map as mutable as it is behind behind a reference. We don't need mute there, we need mute on the type. We need to borrow a mutable. So that should be alright anyways, because yeah, it's just here. And we can actually do something we already did in this series. We can use an extension function for this. And upserter. No, we call this trade upserter. Please define the function. And yeah, we replaced this by a mute ampersand, and then we say impl upserter or a hash map of pos onto num. And then we should be able to use this and say that we simply run a mutable reference to self. And then we have to say self here and self here and go up here and remove that hash reference because we don't need that. And now instead of insert, we simply say upsert. Yeah, this should actually be it. yeah, we simply check, is that position already set? Then get the count and insert the count plus itself, and otherwise just insert it. And in the end, we don't return 0, but we return our starting position dot values sum. I think it already sums as an I64. Perfect. Yeah, we never needed this actually, but it's all right. And I'm quickly going over. It was 40 what we need, I think. Yeah, it was 40. So 40 like this, and then let's run the test. And it actually works. Maybe I sound surprised because these ideas never work on the first try. So let's get over to Brave and copy that in, and it's perfectly correct. Awesome. Nice. So in under 40 minutes, we solved it today. Normally we need around 1.5 hours. This is really, really nice. Okay. Yeah. Then I would already call it a day at this. Yeah. I really like the solution. And yeah, I really liked the task today, probably because we were just so fast with it. And it felt so natural. And yeah, the actual difference to the other days is that I didn't make a stupid mistake that cost us the debugging time. Normally we have to debug so much that it takes so much time. But yeah. Yeah, if you're watching it on YouTube, the recording, or on Twitch, the recording, yeah, I hope you had fun. And yeah, maybe I see you tomorrow in the morning, and otherwise I see you in the next one. Bye.